Hello friends, welcome to my channel. Today we'll be talking about basic maths for machine learning, and we are in the part 2 of our episodes. Okay, so without any further ado, let's talk about basic math for machine learning. So in the earlier episodes, we already have seen what are the definitions of inner product and outer products. Okay, so today we'll be talking about vector norms. So what is vector norms? So norms are basically some scalars that are used to measure length, size, distance or so, depending on the context. First of all, so if we have a vector x in this way, this is a column vector x1, x2 up to xn, we can find out the norm is basically, what is norm? Norm of this vector x is nothing but length, size or distance. So in our plus 2 level, we have seen the formula, right? So if we have 2 points, one is the origin 0, 0 and another one is the point x1, x2 right here. See, this is the x coordinate, so this is the x1, this is the x2 coordinate. So if we have a point x1, x2, then easily we can find out the distance from this origin, right? What was the formula for that? The formula was x1 minus 0 square plus x2 minus 0 square, right? So you all know this formula, the square root of x1 minus 0 square plus x2 minus 0 square. So this is nothing but the norm of the vector x. Okay, so norm is basically a scalar that are used to measure length, size or distance depending on the context. Okay, so now let's talk about different kind of norms that will be used in the machine learning literature. So number one will be used Euclidean norm. Okay, first let me write down the term EUCLI, Euclidean, DEAN. So Euclidean norm. So Euclidean norm is nothing but the usual norm that we have seen in our plus 2 level. Like for an example, the distance between 2 points, just now I talked about here, right? This is nothing but the Euclidean norm. So let's formally define Euclidean norm. So Euclidean norm, which is norm x, the symbol of norm is this, the two parallel line like this way. So this is the definition, this is the representation of norm x. So for the Euclidean norm, we'll write down this square root of x1 square plus x2 square up to xn square. You can see this is exactly the same way here we found. Okay, so this is nothing but we can write down this x transpose into x to the power half. How to get that? This is the vector. If we take the transpose, what would happen? This would be so this is nothing but n cross 1. So we have n rows and one single column. If we take the transpose, it will be 1 cross n, that is 1 row and n column, which is nothing but x1, x2 up to xn multiplied by n cross 1, that is x, which is x1 up to xn. So this is 1 cross n times n cross 1. So which will be, in the product will be x1 square plus x2 square up to xn square. So this is a real number. If we take the square root of this quantity, we'll get back our Euclidean norm. Okay, so this is the definition of Euclidean norm. Okay, I think the idea is pretty clear. Now let's talk about different other kind of norms, and in general we can write down P norm. Okay, P norm can be defined in this way, that norm of x, we already told you this is the definition, this is the representation of norm, this is the symbol of norm, and we will write down a subscript p here, and it will be x. So this is the P norm, and the definition of P norm can be written in this way: summation j equals to 1 to n mod of xj to the power p to the power 1 by p. Okay, it looks scary, right? But believe that it's not that scary. So if we put, think about it, if we put p equals to 2, okay, then let's see what is the form of equation. Okay, if we put p equals to 2, it will be norm of 2, here p equals to 2, it will be j equals to 1 to n mod of xj to 1 by 2. If we further write down this, you can see that this is nothing but x1 square plus x2 square up to xn square. So which is nothing but our normal Euclidean norm that we have defined earlier. Here you can see this is just this one. So this is nothing but our Euclidean norm. Okay, good. Now let's talk about if p equals to 1. Okay, if we put p equals to 1 in this p norm equation, we'll get 1, which is j equals to 1 to n mod of xj to the power 1. So we don't write anything. So 1 to the power 1, which is basically 1. So which is basically mod of x1 plus mod of x2 up to mod of xn. Okay, so this is just the absolute value norm. This norm is called absolute value norm. Okay, so this norm is called absolute value norm. So earlier this norm was called Euclidean norm. This norm is Euclidean norm. This norm is absolute value norm. Okay, now let's put p equals to infinity. Okay, if we put p equals to infinity, it will call a max norm, and it will look like this. It will not be nothing but maximum of mod of xj, and this is called max norm. Okay, so we can see there are mainly 3 types of important norms that we are seeing right here. So if we put p equals to 1, we will be getting absolute value norm. If we put p equals to 2, then this is the usual Euclidean norm that we are seeing from our class 2 level. And if we put p equals to infinity, then we will get a max norm. Okay, so this is the more or less idea of vector norm. So before we leave the vector norm concept, let's talk about few more properties of vector norm. Okay, okay, now let's talk about 2 important properties of vector norm. Okay, so the first property that we will be seeing, first of all, since this represents the distance, the norm of a vector x will be always greater or equals to 0. Either it will be of length 0, or the length or the distance will be positive quantity, that is the non-negative quantity, either 0 or it will be greater than 0. Okay, the second important property that would be, if we multiply a vector with a scalar k, and if we take the norm of the whole quantity k into x, it would be mod of k multiplied by norm of x. Okay, so for any k is a scalar. Okay, so one mistake that generally people does is that they just simply multiply with k, but we should multiply with mod of k. Okay, this one. Okay, so the second property is that if we multiply the scalar with the vector, and if we take the norm of the whole quantity, it will be the mod times the norm of x. Okay, so these are the main 2 properties of vector norm. The next thing that we will be discussing right here, which is the linearly dependent and linearly independent set. Okay. Now, if we have n many vectors, say x1, x2 up to xn, okay, then we call the set of vectors x1 up to xn to be linearly independent, LINER, linearly independent, or LI in short, if and only if, since this is the definition, it would be if and only if the linear combination of these n many vectors, that is c1 x1 plus c2 x2 up to cn xn equals to 0, and that implies ci equals to 0 for all I belongs to n. All I and that implies ci equals to 0 for all I equals to 1 to n. Okay. So if we take the linear combination and if we equate this to 0, and if we solve this system of equation and if we find that ci equals to 0, then we call the vectors x1 up to xn is linearly independent. So on the other hand, what is the definition of linearly dependent, or LD in short? So linear, let me write down, linearly dependent, or LD in short, if and only if, again, if we take the linear combination of the vectors c1 x1 plus c2 x2 up to cn xn, and if we equate to 0, and after that if we find out, if we solve this system of equation and if we find out that at least there exists at least one ci which is non-zero. Okay. If we try to solve this system of equation and if we find out that at least one ci is there which is non-zero, but still the linear combination is 0, we call the system, the set of vectors x1 up to xn are linearly dependent. So these are the definitions of linearly dependent and linearly independent vectors. Let's take few examples. First of all, let's do vector, one vector x we can take as 1 0, okay, and the second vector y we can take as 0 1. Now how to check whether these two vectors x and y are linearly independent or maybe linearly dependent? So what we do, we take the linear combination c1x plus c2y. So we have two vectors x and y, okay. So c1x plus c2y equals to 0. We take the linear combination and we equate this to 0, and our job would be to find out the value of c1 and c2. Okay, let's do that. So c1 times, let's put the value of x, which is nothing but 1 0, plus c2, y is 0 1, okay, and let's again equate to 0. If we just try to solve this, it would be nothing but, so if we just solve this, it would be c1 0 plus 0 into c2 equals to 0. If we do the point-wise addition, it would be c1 equals to 0, 0 meaning here this is the 0 0 vector, right? So if we just compare this, it would be c1 equals to 0 and c2 equals to 0, right? So the solution we are getting c1 equals to 0 and c2 equals to 0. So ultimately, so we can conclude from here that our vector x and y are linearly independent. Okay. So on the other hand, let's take another example, which is x equals to 1 1 and y equals to 2 2. Okay. Now let's see whether these two vectors are linearly dependent or linearly independent. How to do that? First, we start with the linear combination of x and y, which is c1 times x plus c2 times y, and we equate this to 0. Okay. Then we solve c1 times 1 1, just like the earlier one, C2 times 2 2, and here 0 means the 0 vector, right? So if we solve this, we'll getting C1 plus 2C2 equals to 0. Okay, from both equations we will be getting the same thing. Okay, now let's see. First thing that this system of equation has infinitely many solutions, because you can see these two equations. So from here we also get C1 plus 2C2 equals to 0. So these are the same equation. So if we put C1 equals to k, some value of k, obviously k must not be a non-zero value, a non-zero real number rather. And if we put C1 equals to k here, we will be getting k plus 2C2 equals to 0. And from here, C2 will be minus k by 2. Okay, so since k is non-zero, C1 is non-zero, and C2, that is minus k by 2, obviously a non-zero quantity. So we are getting two non-zero value of C1 and C2 for which this equation satisfies. So which basically says that our two vectors x and y is linearly dependent. Okay, I think the idea of linearly dependent and linearly independent set of vectors are more or less clear. Okay, so one thing to note here, so every singleton, every non-zero vector, so if x is a non-zero vector, x is a non-zero vector, if x is a non-zero vector, then implies x is linearly independent. The set x is linearly independent. So if a set contains only one element, only one vector, and which is non-zero, that is, then we call that the set containing only singleton set, which is the non-zero vector, is obviously linearly independent. How to show that? We multiply c into x, we take the linear combination, and here we have only one vector, so c into x equals to 0. And you can see this guy is non-zero, so it says that definitely c must be equals to 0. So a non-zero vector is obviously linearly independent. Okay. Okay. Now let's talk about another important concept. So if we have a matrix A, then rank of this matrix A is nothing but the number of linearly independent column vectors or number of linearly independent row vectors. The same thing. Okay, so the rank of the matrix is nothing but the number of linearly independent column vectors or the number of linearly independent row vectors. We already have seen, so if the matrix A have the element like this, A11, A12, A13 and so on, like A1n, A21, A22 up to A2n, AN1, AN2, sorry, AN2 up to ANN. So you can see this is the first column, right? This is the second column. So first column we can call it as alpha 1, which is A11, A21 up to AN1. Okay. The second column alpha 2, which is A12, A22 and AN2 and so on, like this. So we see in the earlier example, in the earlier definition, we have seen how to check. Now what we do? First we take the linear combination of C1 alpha 1, C2 alpha 2 plus Cn alpha n equate to 0, and we try to see whether this alpha is a linearly independent or not. Okay. Now let's talk about a shortcut rule, how to see whether how to check whether the matrix, what is the rank of the matrix. Okay. So basically in the earlier example we have seen, we need to check the linear combination and we try to find out the value of C and we need to check. Okay. So another very simple way we can check, first of all, if it's an n cross n matrix, first you can find out the determinant of this matrix A11, A12, A13, A1n and so on. If the determinant is 0, then obviously the rank of the matrix is not n, which is less than n. Okay, if the determinant is non-zero, we can say that all the column vectors or all the row vectors are linearly independent. Okay, so this basically says that the rank of the matrix is n, that is the full rank matrix. Okay, I think the idea of rank is bit clear. We can solve one example. Okay, so we can see an example first. Okay, let's take the matrix A formed by the earlier column vectors that we have taken 1 0 and 0 1. We have already proved that these two vectors are linearly independent, right? We have proved in the earlier example that these two vectors are linearly independent, which basically says that, so the rank of the matrix is 2, right? Since the two column vectors are linearly independent. On the other hand, if we take another matrix B 1 1 2 2, we have seen from the earlier example that these two column vectors are linearly dependent. Okay, so what would be the rank of the matrix? Rank of the matrix will be 1. So first, let's consider the space of vector 1 1. Okay, the space containing 1 1. We have already told that if a set of vectors, if a set contains only one single vector, non-zero vector, then the set is linearly independent. So the set constitute of the only non-zero vector 1 1 is linearly independent. So the matrix B has at least one linearly independent vector. So the rank of the matrix B is at least 1, and we can check that these two vectors are linearly dependent. So we can conclude from these two things that this matrix has only one linearly independent vector. So the rank of the matrix would be only 1. Okay, and the way I tried to see that if we take the determinant of A, you can find out the determinant equals to 1, which is non-zero. And we have told that if the determinant is non-zero, the matrix will be full rank matrix, which will be so for a 2 cross 2 matrix, then rank would be 2. And if we calculate the determinant of B, the determinant will be 2 minus 2, which is 0. And if the determinant is 0, then we call the rank is at least the rank of the B. We can conclude here. We can conclude from here the rank of the matrix B is strictly less than 2. And here in particular, we can see the rank is 1. Okay, so this is how we can compute the rank of a matrix. Now let's talk about another important concept of orthonormal matrix. Okay, so a matrix A, let's give the definition first. A matrix A is said to be orthonormal, a matrix A is said to be orthonormal if and only if the column vectors, the set of column vectors are orthonormal. What does that mean? Say if A is a matrix, so A is a matrix where the columns are alpha 1, alpha 2 up to alpha n. Okay, so these are the column vectors. So this is the first column, second column, and so on. So there are n many columns. If this is the vector, so if these are the column vectors of A, we call this set of vectors alpha 1, alpha 2 up to alpha n is orthonormal if and only if any two vectors are perpendicular to each other, any two vectors are perpendicular to each other and they are normal, meaning they are of unit vector, that is their norm unit vector, that is their norm equals to 1. Okay, so one thing, orthonormal means orthonormal implies orthogonal plus normal, meaning unit vector. Okay, so let's talk about this once again. So first of all, this set of vectors alpha 1 up to alpha n is said to be orthonormal if any two pair of vectors is orthogonal, that is they are perpendicular, and they are of unit length, that is their norm is equals to 1. How to see when, what is the definition if we call that two vectors are orthogonal? We call two vectors alpha 1 perpendicular to alpha 2 or orthogonal to alpha 2 if their inner product alpha 1 alpha 2 equals to 0. We have seen the definition of inner product in the earlier video. Now we can see this is the definition of orthogonal. So the orthonormal matrix, the each of the so every two column vectors are orthogonal to each other and they are of unit length. Okay, so this is the definition of orthogonal matrix. So let's try to see what important property of orthogonal matrix. The first property we will be seeing is A inverse equals to A transpose. How to see that? Let's try to calculate this quantity A into A transpose. Okay, so if A into A transpose, this matrix, let's call it as B, this A into A transpose, the ijth element, what would be the form of the ijth element? Ijth element would be nothing but the multiplication of this quantity AI transpose into AJ, right? So this is the form of the ijth element. So if this is the ijth element, we can define this as 1 if I equals to j or 0 if I not equals to j. Meaning what? So if two vectors are the same, if we take the inner product, that would be 1 because this gives the basically the norm. And if we just take the if we just multiply or take the inner product, this is the column wise multiplication is basically the inner product, and if we take the inner product between two vectors alpha 1 and alpha 2, and if this I is not equal to I is not equals to j, that is alpha 1 and alpha 2, then the inner product will be 0 because they are perpendicular by the definition. So if this I not equals to j, it means that alpha I and alpha j are perpendicular, so this value would be 0, else it would be 1. Okay, so if this thing happens, we can see that, so this is basically an identity matrix, right? A into A transpose equals to identity, because all the diagonal element will be 1 and of the off diagonal elements will be the perpendicular of AI and the inner product between AI AJ, and which will be 0. So if this thing happens, we can see that, so what is the definition of the inverse then? We call inverse of B, A into B equals to B into A equals to I. So if we calculate this, we call A inverse equals to B. So this is the definition of inverse. So if A into B equals to B into A equals to the identity matrix, we call the A inverse equals to B. Similarly, here you can see we got A into A transpose equals to identity. In the similar fashion, we can easily compute A transpose into A, which will be again the identity, with the same notation, which will be just change A transpose into AI transpose. Okay, and from here we can easily conclude that A inverse equals to A transpose. So this is one of the important property of the orthogonal matrix or the orthonormal matrix. Okay, so I think the idea is pretty clear now. So what are the things that we have talked today? First of all, we talked about the different kind of norms. There are few different kind of norm. One norm is the Euclidean norm. If there are p norms, so if p equals to 1, it gives us the absolute value norm. If p equals to 2, it gives us So if p equals to 1, it gives us absolute value norm. If p equals to 2, it gives us Euclidean norm. If p equals to infinity, it gives us max norm. Second thing, we have seen what are the definition of linearly independent set and linearly dependent set. So if take the linear combination of the vectors, if the CIs are all 0, we call the set of vectors linearly independent. Else, if there exists at least one CI which is non-zero, we call the set of vectors to be linearly dependent. Then we talked about the rank of the matrix. What is the rank of the matrix? Rank of the matrix is nothing but the number of linearly independent rows or the linearly independent column vectors. Okay, how to calculate that? First, we take the column vectors, take the linear combination equals to 0, try to find out the value of C1 and C2. If all the CIs are 0, we call the vectors are linearly independent, or else try to find out the number of linearly independent subspaces. Okay, then we talked about the definition of orthonormal matrix. What is orthonormal matrix? So A is orthonormal matrix if the columns, all the columns are orthonormal. That is, take any two vectors from that set, and if we take the inner product, that would be 0 because they are perpendicular to each other, and if we take the norm, they are of unit length, that is the norm will be 1. Okay, so this is all for the part 2 of the basic math for machine learning, and in the next part we'll talk about a very important idea which is called eigenvalue and eigenvectors. Okay, thank you.